So we have a chemistry exam tomorrow. I'd like to do a little bit of reviewing. It's basically on kinetics and equilibrium. So kinetics is kind of about reactions, and let's take a look at what this is all about. So we kind of have this regular equation here where we have stoichiometric coefficients in front of the reactants, which become products. And this is just a regular forward-moving reaction. So you basically get a forward rate and just going to put the reactants on this side, and you're going to need some kind of a constant over here, which gives you a slope. And of course, you can do this in the reverse direction as well. So you kind of have like a k1 for the forward, a k -1 for the backwards, and of course, you're going to use the products when you're doing reverse because they're going the other way. And for the forward, you're going this direction. Notice that the rate equation here does not actually include like if we have rate equals k, the coefficients aren't really included in this equation. But notice that there's different ways to write the rate. So if you have the rate this way, realize that it's also could be written like this, where you have the change of this is the change of concentrations. This is a concentration right here, dA over dt. Okay, and then you have 1 over a, which is the stoichiometric coefficients. Notice these are negative because they are draining, as these are positive because they're increasing. So this is kind of the relationship between uh, this rate stuff. Um, and again, so we have this way to write it with the KAB, concentrations to the powers, or we could write it with the stoichiometric coefficient on the bottom times the concentration over time. So that's kind of cool. And what does it help us with? So now we have different orders. So we have like the 0th order where um, the K here, the constant, is basically the only rate. And what I mean by rate is how these things change over time. So this looks like some kind of an exponential rate, I believe. I think it's probably a first order. Now realize that the first order rate here can be written in a different way. So we have like AF equals e to the negative kt with A naught. You could do a little division here if you want to. Um, but we also come up with these rate laws like this. So we essentially calculate the final concentration and then the initial concentrations here. And we have this K, this rate, this this rate constant K, which causes different trends in these lines. And so depending on whether it's 0th rate, you could see that the rate is only equal to K. If we go into the first order, what does that mean? We now have K times the concentration of A. So this is now affecting the rate at any point during the reaction. So that kind of means that here the rate is constant, which means that it doesn't matter how much of the reactants we have, doesn't matter how much the products we have, doesn't matter what time it is, the rate, meaning how quick these things transform into each other, is always constant. But in the first order rate, it depends on the concentration of A, which would be either the products or the reactants, most likely the reactant if you're going forward. And if you go into the second order right here, now we have A squared, or you might have A times B, 2A. Notice how we get, uh, notice how we basically raise the concentration to the power of the coefficient. So we kind of have 2A goes to B, and here we have the rate equals K, A squared. So we have to use this 2, which is the coefficient of A, and raise it to this concentration power and get our rate. Um, now, if you're talking about third order, it's probably not going to happen in one single step. These things can happen in one step if you have first order, second order. What do I mean by steps? I mean by this mechanism in which we complete the reaction. So let's say that there's multiple steps, which leads us to a more complicated equation for the rate of this whole process. Um, we might have this as an example. So R2 equals K2x times C. And we're like, well, that's weird because, you know, maybe the equation that we're looking at doesn't actually include this x. Like it could be a plus b goes to d or something over here. And we're just like, wait a minute, what happened to the x and the c? Because that's what this is all about, right? How did it become a plus b becomes d, or a plus b plus c becomes d? Looks like more like this. A, B, C turns into this d. Well, that's because we had to go through this intermediate process where we started with A and B and we really quickly transformed it into this X. Because it's such a fast process right here, this equilibrium process, we kind of just set it up like this, like in an equation. And we say that X equals KA times B. And then we sort of plug it into the equation for the second one. We get this rate equals KXC. So we got X and the C right here, which makes this, and then we have to have a K2 because the second process. And we're thinking, okay, well, what was X? Because remember in the first equation, we determined that X equals KQ1 times AB. Well, we can plug this in there, right there. And so now we have this, say K2 times KEQ1 uh, times ABC, kind of gives us what we observe. Because we're going to be observing the rate of this whole process, 1, 2, 3 steps, we're going to be observing it as R2. R2 is the maximum rate because it's the slowest rate. All these things, all other ones are fast, so you kind of ignore them, except the first one. The third one you really ignore. The first one matters because you need the intermediate. The second slow one is the one that gives you the rate of the whole process. And so now you observe the K observed, A, B, C, and this is how you observe it, but then you have to realize that this K observed is actually K2 times KQ1. So this is a multi-step mechanisms. And again, we sort of realized the slow rate, the slow step during the multi-step mechanisms gives us the maximum rate of the whole process. Right? It's kind of like the bottleneck, as you can see down here. Um, there might be some other rate laws that we would discover at some other times, but we're just going to focus on the step growth. We take each step as some particular uh, rate, and we focus on the bottleneck, the slowest one. Now we talked about equilibrium for just a second here um, because we want this fast thing to happen at equilibrium. So let's just take a look at EQ for just a moment. That's right here. It's basically when the forward reaction is equal to the reverse reaction, it means that the sum of the rates is equal to 0. And of course the reaction doesn't stop, it does continue, it's just that the rates are the same both ways. Kind of like trading the stock market, it's the same amount of buyers and sellers, the price aren't going to move anywhere. It's not that the market stopped trading, it's just the price hasn't moved. Um, oh, hey, how's it going? Nice, thanks for checking in, Hot Dev. All right, so basically, let's continue. We got the equilibrium. You can see how we solve it. We have to take A, B, C, D, and this is basically A, B on the bottom, meaning the reactants, and then C, D on the top is the product, so A, B, C, D. And this KEQ is equal to the ratio of the forward reaction, forward rate, forward rate constant divided by the reverse rate constant. And we get this little expression over here, e to the power of negative Gibbs energy over R2. That's kind of cool. But we'll talk about the Gibbs energy a little bit later. So for now, we'll just consider that the KEQ is just basically this situation here. And this is for the concentration. It's important to keep the stoichiometry, but you don't want to simplify these things, A, B, C, D, the A, B, C, D, these blue ones. You don't want to simplify the coefficients. You want to keep them the way they are so that you write this equation exactly as it is, A, B, C, D, with their M, N, P, Q exponents. Then we want to start considering, okay, it's KEQ. Are we looking at the concentration version? So we just look at concentrations of A, B, C, D. Are we looking at the pressure version? So now we look at the pressures of A, B, C, and D. And then keep in mind that when we're looking at this KEQ, the rate constant here, uh, we want to be omitting solids and liquids. So we're not even going to count them in this equation. If it's a solid or liquid, we do not put them in this equation. We get rid of it. If it's a gas or an aqueous solution, it goes in. Yes, 100%. Okay, so that happens for KEQ, happens for the KEQ at concentration, and the KEQ for the pressure. But here, we're getting rid of even aqueous. We're just focusing on gases if you're using the pressure version. So this is important. All right, and of course, you can make a little conversion here between the pressure version and the concentration version. Requires a little bit of these other things over here. That's the R is a constant, um, 8.314 joules per mole or something. And then this is the temperature in Kelvin to the power of the change in moles. But that's not as important as realizing that in the rate equation here, the regular rate equation, we include them all. Okay, in this regular rate equation, rate equals this blah blah blah, you're going to include the solids, liquids, the gases, the aqueous, every single possible thing must be included. As you can see, it says include all solids, liquids, gas, aqueous, etc. when you're doing the rates. But when you're building the Q, or sorry, the K or Q, either one of these, the Q or the K, and the Q is the reaction quotient, which is exactly the same thing as KEQ, kind of. Um, but if you're using this thing, then you gotta omit the solids and liquids. None of those. Now Q is very similar to KEQ, it's just that Q is at any time, so it could be at any time you're measuring Q. Okay, you just have to calculate the current concentrations and you figure out what Q is, and you're going to compare that to the equilibrium version of the same formula. This is the exact same formula, yeah? But it's just that this one's at equilibrium specifically and this one's at any time. So you'd have to compare them and then you'll be able to see whether you would expect a forward reaction or reverse reaction, or whether it's actually at equilibrium where K equals KQ. So that's kind of cool. And we've discussed a lot of these things here. We've pretty much covered most of the things we have to know for this test. Uh, Realize that we might be given a table of these rates with initial concentrations and the rates and stuff. So in order to determine these rates, these rates, we need we need experimental data. We can't just come up with this rate equation with the K and stuff without experimental data. We could do it like this, but dA over dt, we don't know dA over dt unless we have the data. So we need experimental data to be able to figure out what the rate is. And so we have to use the initial rates, and you might have R2 equals 2R1. So twice the rate, like 2 times the rate of the first equation. Here's the first one. So the second one is like twice the rate of the first one. And then, oh God, this is some complicated stuff. Let's just forget about all this. It would be better to go through this with an example. Like, notice here, if we have 1 divided by 2 equals a to the power of m divided by 2a to the power of m. Question is, what is m? Well, if this is 1 over 2 divided by 1 over 2 to the power of m, well, then m has to equal 1. See? And if we have 1 divided by 4, 1 divided by 4, R2 equals 4R1, so 1 divided by 4. And then we have this a to the power of m divided by 2a to the power of m. What's the m? If we want this to be 1 over 4 equals 1 over 4, then it turns out that m has to be equal to 2. Otherwise, we don't get a 4 on the bottom. So that's how we get this. We have to solve it like that. And again, this requires experimental data where you kind of have you're sort of changing the concentrations and stuff. And we also have to consider disturbing equilibrium at Le Chatelier's principle. Um, if we're increasing the concentrations of the reactants, A goes up, then if we have more of A, then that kind of forces more of the products to show up. And according to this, it looks like KEQ goes up, but it seems to be a little bit strange. I would assume that if you increase K, the A, then KQ goes down. I'll have to do a little bit of research on that one. But let's look at this one here. So pressure, if we raise the pressure or decrease the volume, both of them have the same effect of increasing pressure. And what happens is we have to only consider like the gases. And we have to go to the side that has the least amount of moles of gas. So like, here's a little equation here. Let's say you're looking at this and they both have the stoichiometric coefficients of 1, 1, and 1. And let's say that, they're all gases, A, B, and X. The question is, which side has the least moles of gas? And the answer is the right side because there's only 1 mole of gas here and there's 2 moles of gas here. So as you increase the pressure, it's going to force this equation more to the right side and you're going to get more X. As you increase the pressure, you kind of go to the side with the least moles of gas. Now, if this was a solid and a gas goes to a gas, then it's the same amount of gases on both sides, meaning it's not going to do anything. Okay, and then let's look at the temperature, for example, here. If we increase the temperature, then we got to know whether it's endothermic or exothermic, meaning whether H is positive or H is negative. And if the the endothermic means that the heat is part of the reactants. Exothermic means it's part of the products. And so if you're raising the temperature and the heat is part of the reactants, it makes sense that you're adding more reactants, and then you're going to get more products on the other side. And hence KV goes up. I guess it's the same logic that we're having over here. But if the temperature goes up and heat is part of the products, then clearly you're going to get more reactants out of there, and KQ goes down. All right, so we've kind of talked about all that. And the only other thing we might want to consider here is perhaps this Arrhenius equation and the activation energy. So you kind of have this amplitude here, ln of A, and then you can kind of do this e to the power of negative A over RT. Remember that R is a constant. The EA is the activation energy. If we look at these graphs over here, we can see that if we're in a forward reaction like this, the activation energy is quite large. In endothermic, we end up over here. And if we go over to an exothermic reaction, we have a smaller activation energy this way, and we kind of end up down here below. So this is basically how we would want to do that. Calculate K using the Arrhenius equation, or the 2-point Arrhenius if we have more data. And that's essentially it. We can kind of write these equations a little bit differently over here, considering the Gibbs free energy. And the Gibbs free energy basically just tells us what direction the equations, the reaction is going to go, based off the Gibbs free energy. Kind of points you in the direction, one or the other. But we haven't really gotten too much into that, so we'll just kind of ignore that for now. Here's another interesting thing that might help us with concentrations is it's also related to absorbance. But yeah, so that's basically it. Let's kind of review this one last time. The main things, we've got reaction rates, forwards and backwards, the concentrations, we get the reaction quotient, KQ, concentration and pressures, the Chatelier's principle, order of the rate. That's just basically found by the rate equation K times K times A squared, or KAB. Is this unimolecular or bimolecular or zeroth order? There were multi-step mechanisms. We have the Arrhenius equation and activation energy. So this is pretty cool. Some relatively simple stuff to get